the Clausius-Clapeyron equation allows us to calculate the temperature and vapor pressure. So in this equation, there are two pressures and two temperatures. Here we can just use the high pressure cooker as an example. We know that at 1 atm, the boiling point of water is 100 Celsius degree. So the P1 equals 1 atm and T1 equals 100 Celsius degree. But in this equation, we always need to keep the temperature in Kelvin. Then, if we know the pressure that a high pressure cooker can reach, then we know P2. From this equation, then we can calculate T2, which is the boiling point of water under P2 pressure. And the T2 is generally higher than the 100 Celsius degree in this case. When we use this equation, we need to keep the R. We need to keep R, this value, and then the delta H VAP is the enthalpy of vaporization, and then delta H vap must be in joule for use. In this equation, the delta H vap is constant. That means it's independent of temperature, but we know the enthalpy of vaporization could vary as temperature change. So this equation is an estimate, is very good, can give us a very good estimate. Now let's talk about the typical heating and cooling curves. A typical heating curve for a substance always shows changes in temperature that result as the substance absorbs heat. The cooling curve is generally the same as a heating curve, except in an opposite direction. Let's use -10 Celsius degree ice as an example. For an ice of -10 Celsius degree, as it absorbs heat, the ice starts to increase in temperature. Before its temperature reaches 0 Celsius degree, the ice is still a solid ice, is still in solid phase. When the temperature reaches 0 Celsius degree for the first time, the solid begins to melt. Then there's a mixture of solid ice and liquid water. However, before all the ice melt, the mixture will maintain its temperature. The reason is because if there's ice, the ice will absorb all the heat. And for a mixture, the temperature should be the same throughout the mixture. There's no way for an ice to be above 0 Celsius degree. That's the reason why the mixture maintains 0 Celsius degree. As heat is provided to the mixture, all the ice will be melted. Then the mixture becomes a pure liquid. Okay, and then the liquid can increase its temperature as more heat is provided, and the liquid water can increase its temperature from 0 degree to 100 Celsius degree. When the temperature reaches 100 Celsius degree, some of the liquid water evaporate. then we get a mixture of liquid water and water vapor. Similarly, the temperature here will maintain 100 Celsius degree because no liquid water can have a temperature higher than 100 Celsius degree. Then for this mixture of liquid water and water vapor, the temperature can only be 100 Celsius degree. As more heat is provided to heat the mixture, all the liquid is evaporated. Then there's only one phase left, which is water vapor at 100 Celsius degree. As more heat is provided, then the water vapor can increase its temperature above 100 Celsius degree. It can, for example, here you can reach 120 Celsius degree for water vapor or water gas here. So for the cooling, it's very similar, except that it starts from the high temperature water vapor or water gas, and then the cooling curve is the same as the heating curve, except that these two curves are opposite in direction.